Good morning students. Now I discuss about frequent pattern growth. First one, contents of the topic: FP-Growth algorithm, FP-tree construction, FP-tree size, conditional FP-tree, benefits of frequent pattern, FP-Growth versus Apriori, construct FP-tree, challenges of frequent pattern mining, software for association rule mining. The first one, FP-Growth algorithm. This algorithm uses a comprised representation of the database using an FP tree. Once an FP tree has been constructed, it uses the recursive divide and conquer approach to mine the frequent item sets. The two building of FP tree: first one, scan data to determine the support count of each item. Infrequent items are discarded while the frequent items are sorted in decreasing support counts. To make a second pass over the data to construct the FP tree, as the transaction are read before being processed, their items are sorted ascending according to the above order. Next one, the first scan of the frequent pattern growth. The two columns to be separated: first one transaction ID, second one items. The first transaction to 10 transaction. First transaction is A comma B. The last transaction is B comma C comma E. The supporting value B is 8, A is 7. The counting supporting value of C to 7, E 5, E 3. Next one, FP tree construction. After reading transaction ID 1 to 10, the first one transaction ID 1, the starting value is null, A comma B is pair. The A is first one to implement, but B is greater, supporting value is 8. So B is first implement and A is second implement. Null B equal to 1, A equal to 1. First after reading TID 1. The second one, TID equal to after reading 2, B, C, D. Already B is 1. To calculate the again 1, B2, A1, C1, D1. This is a FP tree construction. The final, after final the transaction ID BCE, the same process to implement the FP tree construction. The B equal to 8, A equal to 7, C equal to 7, D equal to 5, E equal to 3. This is a supporting value of the 10 transaction ID pair. The chain pointers help in quickly finding all the path of the tree containing some given item. The next one, FP tree size. The size of an FP tree is smaller than the size of the uncompressed data because many transactions often share a few items in common. The two scenarios to be represented FP tree: best case and worst case. The best case means all transactions have the same set of items and the FP tree contains only a single branch of nodes. That is best case scenarios. Next one, worst case means every transaction has a unique set of items. As none of the transactions have any items in common, the size of the FP tree is effectively the same as the size of the original data. The next one, the size of an FP tree also depends on how the items are added. If the using ordered scheme in the preceding example is reversed. The next one, FP growth. The FP growth generates frequent item sets from an FP tree by exploring the tree in a bottom-up fashion. Given the example tree, the algorithm looked the frequent item sets ending in E first, followed by D, C, A, and finally B. Since every transaction is mapped onto a path in the FP tree, we can derive the frequent item sets ending with a particular item. Say E by examining only the path containing node E. This path can be accessed rapidly using the pointers associated with node E. To generate the path containing node E, after the transaction TID 1 to 10, the final construction the tree is to represent yellow diagram. The final path containing node A to E to be represented in blue color. The next one, conditional FP tree for E. To build a conditional FP tree for E, which is the tree of item sets ending in E. It is not the tree obtaining in previous slide as a result of deleting nodes from the original tree. Next one, to construct a FP tree, this is representance of the blue representation, the set of path containing E. Insert each path after truncating E into new tree. That is the header table item pointers. The new construction of tree represents C value 4 pointers, B is that is 3, A is 2, D is 2 to calculate this tree. The conditional F tree for E, the yellow color representation, the path of conditional null value to E representation. Adding up the counts for D, we get 2. So E comma D is frequent item sets. We continue recursively because base of recursion when the tree has a single path only. This is a FP tree constructions. Next one, benefits of FP tree structures. The two benefits, first one completeness, second one compactness. The completeness, the complete information for frequent pattern mining. They never break a long pattern of any transaction. Next one, compactness. To reduce irrelevant information, infrequent items are gone. The items in frequency descending order, the more frequently occurring, the more likely to be shared. Never be larger than the original database, that is not count node links and the count field. This is the benefits of FP tree structure, that is completeness, compactness. Next one, recursion of FP tree. The recursion to be represent the path pattern base AM and CM and CAM. That is the M conditional FP tree. The null values FC supporting value 3, F of 3, C of 3. The recursion of represent F of 3, the null to derive the F of 3. Next one, the conditional of CAM to represent supporting value 3, the null value F of 3, C of 3, A of 3. Next one, special path of single prefix path in FP tree. A conditional FP tree T has a shared single prefix path P. Mining can be decomposed into two parts. Reduction of the single prefix path into one node. The concatenation of the mining results of the two pods, that is null values A1 to N1, A to N2, A3 to N3, B1 of M1, C1 of K1, the association of C2, K2, C3, K3. The association of R1 equal to null values to separating A1, A2, A3, N1, N2, N3 plus another decompose the parts R1, B1, M1, C1, K1, C2, K2 and C3, K3. This is a decomposed of mining. Next one, mining frequent patterns with the FP tree. The two frequent patterns of FP tree, first one idea. The frequent pattern growth recursively grow frequent patterns by pattern and database partition. The methods of frequent patterns. For each frequent item, construct its conditional pattern base and then its conditional FP-tree. Repeat the process on each newly created conditional FP-tree until the resulting FP-tree is empty or it contains only one path, and single path will generate all the combination of its subpath, each of which is a frequent pattern. Next one, the verses of Apriori and FP.Growth to represent the scalability of threshold. This diagram to represent Apriori and FP.Growth threshold representation. Next one, why is FP.Growth the winner? The divide and conquer to decompose both the mining task and DB according to the frequent patterns obtained so far leads to focused research of smaller databases. The other factors: no candidate generation, no candidate test, compressed database, FP-tree structure, no repeater scan of entire database. Then basic herbs counting local frequency items and building supporting frequency pattern tree, no pattern search and matching. Next one, challenges of frequent pattern mining. First is challenges: multiple scans of transaction database, huge number of candidates, religious workload of support counting for candidates. The improving a priori general ideas to reduce the process of transaction database scans, string number of candidates, facilitate support counting of candidates. These are challenges of frequent pattern mining. Next one, software for association rule mining. Special software for association rule mining: Angus, Carton Morse, Ghost Miner, Intelligent Miner, JDA Intellect, Mantos, Mindset, Mining Mod, Oracle, and Vega 3. There is special software for association rule mining, Vega 3. Thank you, students.